Okay, we are on page 34, and we're just doing a quick review of ionic compounds because you learned covalent over the weekend, and I want you to remember that we have to know both. What are ionic compounds made of? Ionic compounds are made of ions. What kind of ions? Positive and negative. What are they called? What do we call positive ions? We call them cations. And the negative ones are called anions. Hopefully by this point you know those already, but just in case you have forgotten, we have two little mnemonics. We've got this cute little cat who's showing us his paw. Cats have paws, so cations are positive. We have a negative ion, or onions make you cry, which is negative. Now, if I have an ion that just has one atom, Na plus, Ca 2 plus, Fe 3 plus, Fe 2 plus, just a single atom. Do you remember what we call those ones? Anyone remember the prefix for one? Prefix for one is mono. Okay, so mono means one, and these contain one atom, so they are called monatomic. Monatomic ions. Anyone remember the prefix that means many? Poly. So if we have an ion such as NH4 plus, that contains both nitrogen and hydrogens. In fact, 1 nitrogen and 4 hydrogens gives us 5 atoms in total. So that is a polyatomic ion. So we might have monatomic cations and monatomic anions. We can have polyatomic cations and polyatomic anions, CO3 2 minus, NO3 2 minus, or sorry, 1 minus, and CrO4 2 minus. Cations and anions stick together because positive and negative, what do they do to one another? They attract. That attraction is called electrostatic attraction. Electrostatic attraction is a force between charged particles. Do we all remember a crystal lattice? Tell your partner, what is a crystal lattice? A crystal lattice is alternating positive, negative, positive, negative, positive, negative, positive, negative, positive, and you could draw a single slice of it like this. And the attractive force in between that strong electrostatic force is called an ionic bond. What do we call a single unit of an ionic compound? That is a formula unit. So that would be, if we were to take our little slice here and we took just one positive and one negative, that would be a formula unit. So hopefully most of this page has been review, okay? Most of it anyway. All right. Ions are particles. Ooh, do you remember the 4 types of particles? See if you can tell your partner the 4 types of particles we've learned. Not subatomic particles like protons and electrons, but just particles. What's one type of particle? Molecule. What's another type of particle? Atom. What's a third type of particle? Yes. Formula unit. And fourth? An ion. Yeah. Okay. And actually, if you have more than one atom, that can make a molecule. So atoms make up molecules. Ions make up formula units. Yeah? Okay, can you fill in this next line? The prefix mono means 1. Therefore, monatomic means 1 what? Atomic. Monatomic means 1 atom. Poly means many. Polyatomic means many atoms. All right, and if we had a polyatomic ion, it might look like this. We might have a Cl attached to an O, attached to an O, attached to an O, and that whole thing has a negative charge. That would be an example of a polyatomic ion. That one's made of 4 atoms with a charge. So it's kind of like a molecule with a charge, a polyatomic ion, kind of like a molecule with a charge. What does MC stand for? Molecule. Okay, so what you're going to do is remembering that every element starts with a capital letter, and the little numbers down below tell you how many. You're going to say if this is a monatomic ion, if it is a polyatomic ion, so is it monatomic? Is it polyatomic? Or is it not an ion at all? How about this first one? Let's do the first one together. Is it monatomic? Is it polyatomic? Or is it not an ion at all? It's monatomic because we just have Na. There's no little number at the bottom, so that is monatomic. And if it is an ion, which it is, let's also indicate if it is a cation or an anion. Is this one a cation or an anion? That is a cation. And if you'd prefer to write out a little bit more than M and C, you can write mono, cat, or you can just write M and capital C. Do you guys think you could try the rest of them now? Give the rest of them a try? Okay. I'll come around and take a look and see how you're doing. So there's two modules. Doesn't have a charge. Charge. So is it an ion? So it's not an ion. If there's no charge, it's not an ion. Folks, if there's no charge, it's not an ion. Okay? No charge. Yeah, exactly. That's exactly one. That's an ion. Okay. Yeah, but I am saying not. Okay, so cations are positive. Okay, so cat is positive. Cat is positive. Yeah. Anion. That's an anion. Yeah, there's only one capital. So mono and there's no charge, you can just write on that. Yeah, just on. Okay. Very good. This one, there's only one capital letter. There's only one capital letter. So I have many atoms or just one atom. Just one atom. There's two capital letters. 17, 16, throughout the name. One, so it's mono. Two capital letters, so it's all right. Okay, let's go through quickly, check them together. H3O plus is a polyatomic cation. Cl minus is a monatomic anion. NO3, there's no charge up there, so that is not an ion at all. It is neutral. NaNO3, again, there is no charge. It is not an ion at all. And same thing with this one here, not an ion at all. CO3 has two capital letters, therefore it is poly. It is negative, so it is an anion. Jerry, welcome. I'm very excited to have more students in my class. I got hardly anybody now. Okay. All right. And CO, there's only one capital letter, so that's monatomic. It's positive, so it's a cation. And if you want a better way, if you want a different way to remember cation, C-A-T, cat. What does this letter look like? Looks like a positive. Yeah? And anion has an N in the middle, and that's negative. Okay? All right, so that's a monatomic cation. We have a non, and then we have two capital letters, so that is polyatomic. And it's negative, so that's an anion. Okay, an ionic bond, this is number 4, is due to the, and it's a word that starts with E. Electrostatic. Attraction between a cation and an anion. So here's how the compound forms. This should look familiar now. We have sodium, which is the electron giver, which is the metal. And we have chlorine, which is the electron taker, which is the nonmetal. Which one of those, this is enriched, but which one of those would have higher electronegativity? Chlorine. Higher I'm just going to say electroneg because it's such a long word. And this one is lower. And when we're in grade 11, we actually get to the point where we just call it EN for electronegativity because that's just such a big long word. And we end up with a positive ion, a cation, which is the metal, and the negative ion, which is the non-metal. And everybody is most stable because it has a full valence shell, and we should all know how many electrons fill up shell number 1? 2. How about shell number 2? 8. Shell number 3? 8. Okay, so you can fill those in at the bottom of the page. And now we're on to page 36. Nature loves the most stable state. So if you have something that is less stable, it is naturally going to go to a state that is more stable. Now, quite frankly, it would probably collapse in a pile. It wouldn't quite look so tidy and organized. But this process here doesn't happen unless you throw in some energy. Okay? It's kind of a little more obvious if we look at this next one. This is unstable. Is this high potential energy or low potential energy? High potential energy. Okay, and this guy over here, this one, it has gone to the bottom of the hill. This is now stable. Is that high or low potential energy? Low potential energy. Can I just write PE for potential energy? PE, potential energy. When the ions are apart from one another, if we have a positive and a negative and they're apart, this is a high potential energy. Unstable. This is when they're right together, that is low potential energy, and that is stable. So if you have a positive and a negative, and you put them near each other, they will naturally move towards each other. If you want to split them apart, you have to put in energy. You have to rip them apart, right? You would have to grab one and grab the other and go, "Ugh," right? They won't naturally fly apart. Just like the ball at the top of the hill. It rolls down naturally. But if the ball's at the bottom of the hill, is it going to roll up the hill all on its own? No, you would have to put in energy. You would have to get under that ball and push it up or carry it up. So you would have to put in energy. So sodium and chlorine. This is Na, neutral, Cl, neutral. That is unstable, Na plus, Cl minus, and they're stuck together. What do we call that? That thing that sticks them together. That's an ionic bond. Now this word Spontaneous. How many of you know the word spontaneous? Okay, spontaneous basically means it happens naturally. So every time I'm saying it happens naturally, what I'm really saying is that it is spontaneous. So going from less stable to more stable, that is spontaneous. And energy is actually released. And if you're like, well, how is energy released? We can think about it this way. For if I have this pen that's up here and I drop it, you can actually hear some of the energy come out as sound energy. Yeah. The pen will actually get a little bit warmer because the particles will be moving faster because they bashed into the desk. So it has released some heat energy. Okay. And let's say you had water flowing down a hill. Okay, same thing as moving from high to low potential energy. You could put a water wheel in the way and it would turn the water wheel, and you could actually use that to even make electricity. That's how hydro dams work. Okay, so when we talk about BC Hydro, that's our power source. The water flows down the rivers and they go through some turbines, and through the magic of electromagnetism, you can turn that mechanical motion into electricity. Basically what they do is they get, as the water goes down, it spins these things and the things are magnetic. And when you have magnets that move, it actually creates electric current. So that's how they turn it into electricity. It's very cool, actually. But anyway. So bond formation is spontaneous. This is bond formation. And if energy is coming out, we have a word for that. Again, this is an enriched word. We call it exothermic. Now, what the heck? Thermic. Are you familiar with the word thermal? Thermal meaning kind of like heat. Okay, so we have heat and we have exo, which means the energy exits. So the energy is coming out of the system as heat. So bond formation is exothermic. And I really need to write myself a note to bring in my sodium because I'd like to show it to you tomorrow because it is a beautiful exothermic reaction. Bring sodium. Okay? Now, just like if we have to roll the ball to the top of the hill, this is non-spontaneous. We have to put energy in. It requires the input of energy. That's going from more stable to less stable. And the same thing is happening. If we rip those ions apart, we have to put energy in. So bond forming is exothermic. Bond breaking is what we call endothermic, which means that heat enters the system. So again, the thermal means heat. Endo, enters. All right, let's see if you can fill in the blanks on the next page. Ionic bonds. We have a transfer of electron from, how about you tell your partner, where does the electron come from and where does the electron go to? Where does the electron come from? Where does the electron go to? Goes from the metal to the non-metal. So who is donating the electron? Metal. Who is taking the electron? Non-metal. The positive ion is called a hat ion. Remember, it's got that plus sign in the middle of it. And the negative ion is called an anion. What do we call that force of attraction? It's very similar to electromagnetic, but it's actually electrostatic. Okay, electromagnetic is it's a different force and it does involve magnets as well, okay? And once you have that electrostatic force of attraction, we get the ionic compound, we get this structure, which is called a crystal lattice. And we have, although in reality, you will never get a single unit of an ionic compound. You'll always have a crystal lattice, but we still give this single unit a name. Tell your partner, what is that name? Formula unit, yes. Okay. In neutral atoms, the number of what equals the number of what in neutral atoms? Protons, yep. Equals the number of electrons. And therefore, the net charge is 0. So in sodium, we have 11 protons and 11 electrons, and the net charge is 0. Chlorine, we have 17 protons. How many electrons? How many electrons? 17. We have 18 neutrons, okay? And the net charge, therefore, is 0. Don't forget, I know this was from our last unit, but the mass number is at the top. That's the protons plus the neutrons. And the atomic number is at the bottom. And that is the number of protons. Could you please write in the mass number and the atomic number for sodium and chlorine? Okay, there's our sodium, there's our chlorine. Could you write in the mass number and the atomic number? Carson, do you know the atomic number of sodium? The atomic number? Yeah, 11. Beautiful. And Kimmy, do you know the mass number of sodium? You forgot? The mass number is the protons plus the neutrons. So what would our mass number be there? We have 11 protons and 12 neutrons. 23, beautiful. And that goes up at the top left. Excellent. Okay. Tristan L., what is the atomic number for chlorine? Atomic number for chlorine? Sorry? Cl is the symbol. How do we know the atomic number? The atomic number is the number of protons. So what is the atomic number for chlorine? 17. And Oscar, where does that go? What corner? Does it go at the top right? Does it go at the bottom right? Top left? Bottom left? Bottom left, yes. Okay, good. So we have our number of protons, 17. Ella, what is our mass number? 35. 18 plus 17 is 35. And Angela, where does that go? Up. Yep. 35. Excellent. Okay. So here we have the formation. Whoa, look what happens to the size of the sodium ion. It went from being pretty big to being pretty small. Have a little chat with your neighbor. Why might it be that sodium went from being big to being small? Yeah, for sure. Why did sodium get smaller? Why? No, you know. Tell me. It loses an electron, but not just any old electron. It loses an electron in shell number. The outer shell. Is there anything left in the outer shell after that? No. So in essence, it is losing an entire shell's worth, yes? So it used to be the size of shell number 3, but now it's only the size of shell number 2. Okay? And if you're planning on taking any of the enriched chemistry courses, we would say it has, since it lost the outer electron, it has one less occupied shell. Okay? So fewer occupied shells. Why did chlorine get bigger? It gained an electron, yes. Okay. This one up here lost an electron, there's fewer occupied shells. So it gained an electron. Did that electron go into a new shell? Let's take a look at the outer shell of chlorine. Here's chlorine. Chlorine has 17. Oh my God, do I have to draw all of them? Okay, I guess I will. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17. Where does the incoming electron go? It still goes into that same shell. It goes into that empty spot right there. So we don't actually gain a new shell with chlorine. But what are we putting close to each other? We just put another electron close to an electron. And what do electrons do to one another? They repel. And we call that electron repulsion. So the extra electron repulsion makes Cl minus bigger. Why will it not? Let me just draw a dot. That's okay. There we go. Okay, so let's go back up here. A single unit of NaCl is called a formula unit. Yep. And the 3D structure is called a crystal lattice. Are you getting tired of this vocabulary yet? Hopefully. By the time you get tired of it, that means you start really knowing it. Do you know what I mean? If you're like, oh my gosh, it's a formula unit, Ms. Benz, why are we doing this again? Then you really know it. When ions form, what is lost or gained? It is always what particle? Electrons. That are lost or gained, but we do never lose or gain protons. Otherwise, it becomes a different atom. Okay, cool. Oh my God, does this keep going? Lordy. Oh. I think we need a 5-minute break. Don't we need a 5-minute break? Would you like to go outside in the sunshine? Let's go outside in the sunshine. Okay?